And he said he'd pick me to do the after lunch thing to be really exciting. So I'm going to talk like this as a really, really dynamic speaker. But it is an exciting topic, lens flare, right? It seems like we should be able to get rid of it pretty easily, right? Like it makes these stars. It also makes this kind of blurring around the sun. It causes all sorts of problems with glare evaluations, figuring out how big the glare source actually is, what's part of the sort of circumsolar sky and what's coming from the camera, what's coming from the roller shades, what's coming from the camera. But it's very dependent on the lens, on the aperture, on where in the field of view it is. And so there are ways that you can algorithmically try and get rid of it. But the best thing to do is to just keep the sun from even entering into the optics. So yeah, just kind of quantifying the problem. If we have image on the top, typical image, HDR image taken, we get this kind of lens flare area that is hiding everything that's going on there, but is also, because of these diffraction spikes, is spreading out across the image. And so has a far-reaching effect, especially if you're concerned about the things you might be looking at. If you're using the HDR, not just for illumination, but also view, it's not a very pleasant artifact. If we compare that to the image at the bottom that doesn't have lens flare, we can actually kind of see the scale of the problem. And so there's kind of three different layers going on. I guess I'll use the mouse for online, right? There's the near source flare, kind of this bubbling out and spilling over of light. And then we have the diffraction spikes. And then there's this blue hexagon there that's actually a re-reflection, kind of going back out to the lens and then coming back in through the aperture. So to try and clean all that up with just software would be, I don't know. I tried it for a minute and it was too hard. Maybe somebody else can do it. And yeah, so we've got the flare, it's sort of near kind of blobby flare, and then the diffraction spikes, and quite significant. You know, we're up in the it's that 100,000 candelas per meter squared into 1 degree. I can't tell you what happens inside of that because of my reference, which is what the presentation is about. But it's all there. So hardware-based solution. This is the Camera Shadowband that I got sort of fabricated, worked on the design. And so the idea is that with 2 axes of rotation, we can cover the entire kind of angular fisheye or entire hemisphere in 2 different ways. And so we have a lot of redundancy there. Well, actually, I mean, in 2 orthogonal ways. And so here's kind of how it moves. Here are these 2 axes of rotations, and then this is also going to show you what the sequence is for capturing an image. So first we use a little bit of ND filter to capture the direct sun. Then we can capture the hemisphere with it oriented vertically and then horizontally. It's a little fast, so I'll do it one more time, right? So moves up and down, this side to side. No. This is stop motion. And that's the next step. Well, maybe not the next step, but that next step. Yeah. So yeah. Yeah. And so then here's kind of the capture sequence. This would be on the left is a kind of traditional capture where we put an ND filter behind the lens and so we have a full field ND filter. Which then means we actually need to go up to very long exposure times. And so that image takes about 60 seconds to capture, going up to a 30-second exposure to get all the way down to the dark shadows without a lot of noise. Or we can take 3 different images. So we take one of just the direct sun, and that takes less than a second because we don't actually need all those exposures. So we can just go and take those and then adjust the vertical orientation. Now, we don't have an ND filter, which has advantages in color matching, but also has advantages in that we don't have to go to as long of an exposure. The longest exposure is only 1 second. And so altogether, it takes about the same amount of time, right? You need a little bit more practice, but you can also kind of capture a full sequence in about the same amount of time, in a minute or less, depending on how quick you are at aligning the shadow band. And so actually it's surprisingly easy to align because of the diffraction spikes, because if you look on the live viewer, it just disappears suddenly. And so you'd think it might be hard, but it was pretty quick and took about 4 or 5 sequences to like get the feel of it. So then to blend away the shadow band, we start with the solar position. So just find those brightest pixels in that image, and then from that single point, and then knowing that this arcing band is going to project as these kind of profile angle like curves, we know where the shadow band is from just that one point. And so then we can make a blending mask and use the horizontal where it's to get rid of the vertical shadow band, and use the vertical to get rid of the horizontal. And then we can kind of blend it all together like this and get everything really nice and flare free, except for that one central spot where the two band images intersect. And so here we're just kind of zooming in on the intersection. The blending steps down, so you don't start, because sometimes it's not perfectly aligned. And you can get into this, like basically into this 2-degree zone around the sun. You can get pretty nice imagery, and then everything in there potentially has a little bit of flare, has the black area. And so this area, this green or white area, needs to be either interpolated or extrapolated to fill. Now the shape of that intersection changes depending on where the sun is in the field of view, because you both need like a 2-degree circle around it, but then also as the intersecting angle between the two bands gets more acute, this diamond shape kind of stretches out. So using that as the mask together. And I realized that if you oriented these always perpendicular, you could do a lot better. But then algorithmically, that's a little harder, because then you have to precisely know where those shadow bands are. So it's a bit of a trade-off, but with an automated motorized version, it would probably work pretty well. So for filling in this area, there's first kind of an interpolation of using this area around, so just like all of those pixels that are right on the edge, and then just interpolating into the center. But then also knowing that, like if it's a clear sky condition, knowing that it's getting brighter as I get closer to the sun, we can also extrapolate into that. And so the algorithm does a quick regression on these points, and if the slope is sufficiently strong towards the center, then it will actually extrapolate up and kind of add a little bit of that energy, or add intensity there, but making sure that the energy stays balanced. And then I guess I missed that slide. And then you take the, oh, here it is. Add the sun from the ND filter image energy, and then just assume that it's the proper solid angle and plop an even colored dot on there. So it's quite a bit more like a rendered image, as opposed to what the ND filter image that's going to have quite a bit of chromatic aberration and some differences in luminance intensity. Like we can mostly assume that the luminance is even, and we know how big the sun is, and so we just plop a little spot onto the image, or we can leave it off and then write it as an environment map and then use it in rendering as the source. And so that's kind of another nice thing, is it's really easy to like extract that peak source out of the image. So as far as illuminance accuracy, this is from a sample data set of about 200 images taken around Lausanne in all different orientations and conditions, cloudy skies, clear skies. acute angles, varied angles that we collected last summer. And so and then it's compared, the illuminance is compared to a handheld illuminance meter taken both before and after the HDR capture sequence, as well as a camera-mounted secondary illuminance meter, so that we can sort of have a comparison of like two other devices as a between-device comparison, because it's often, like there's a lot of uncertainty in lighting measurement. And then I also used pyranometer data from about never farther than 8 kilometers away. And so filtered that down to just the sets where there weren't clouds and there was consistent solar radiation to estimate the solar luminance. And so there's a little bit of, so there's about 100 images that didn't have the sun in the field of view, either because it was overcast or images were pointing in a different direction, and 100 with the sun. The between illuminance meter measurements is pretty consistent, as you'd expect. They're not calibrated against each other. So there's about a 3% bias there. And then there's a slight sort of positive bias for the no sun condition, and then a slight negative bias for the sun condition, which could be the result of any number of things, because there's aperture correction, shutter speed correction, color shifting, as well as the shadowband merging process, but it seems like it's not that part of it. But overall, the absolute deviations, and again, the HDRs are also not calibrated to this illuminance meter. They were calibrated against a different device. So these are all sort of completely independent. And so overall, like pretty successful as a lighting measurement device, and with average deviations below 10% across all these cases, which seems pretty good. And so then here are kind of the results highlighting some of the like images that came out well and some of the images that didn't come out as well. And so even with the shadow band, it's still really important that the lens is completely clean, because if the shadow band only blocks that direct view to the sun, but if there's dirt on the lens, that will cause some secondary scattering. So you can get some scattering around here. Also, the interpolation tends to fail if there's a really strong asymmetry. So here there's a cloud right at the edge, and so I kind of got this blown out region there that looks wrong. Depending on the cloud position, you can get kind of lucky and it looks pretty good, or you get kind of this weird bow tie effect. When it's really eccentric, that interpolation area gets big, and so that is more likely to run into trees. But if you don't have trees there, then you can get a pretty nice result. And then same thing with clouds moving. Like if the clouds are moving quick, but you get lucky, it looks okay. But if they're moving quick and it changes quite a bit, then you'll get some weird artifacts. Now, all these artifacts are right around the sun, and so depending on what you're doing with the image, that might not matter, because the illuminance is still pretty good. And so as a light source, it's still good. It's only if you're directly looking at that. But if you're going to like use a tone mapping, that's mostly all going to be out of range and bright. And so like this image looks good. And so that's why these images are all exposed pretty darkly. And so the idea behind all of this is I was trying to collect these environment maps data set to do some view visibility analysis in kind of hybrid simulation stuff, which I'll show a little bit more of tomorrow. But I also wanted to see how it might work for indoor applications. And so here's a view through Venetian blinds. And then, like you've got these obstructions right by the sun. So there's kind of a weird thing going on in the interpolation. But if the shadow bands are located really precisely, that can be minimized by kind of shrinking that radius, especially when you're towards the center of the field of view. As it gets more eccentric, it's more likely to have some errors in the lens projection and things. But with kind of bespoke custom picture by picture refinement, you can get kind of really nice images. And so for Venetian blinds, that's not, don't really get anything so interesting. But what's pretty cool is with something like roller shades, now we can actually disentangle the flare that's there and is actually present in the space on the fabric from the lens flare that's just an artifact of the capturing method. And so by kind of minimizing it in there, we can really get a sense of like what's actually coming off of the fabric and like how much of that is that bright spot in the middle due to the lens flare versus how much is getting scattered by the shade fabric, which I will also take advantage of in what I present tomorrow. So I did that super quick. So hopefully people have questions, but I want to thank the PLT team who did the fabrication. I wish I had brought this device. It's anodized aluminum. Like it's beautiful. Like I was expecting, I don't know, the first model I made was out of paper and it like worked. I was like, okay, here's what I need. And then they crafted this amazing thing. And then Esteban Herman was this amazing intern, 19 years old, went out and took all these pictures in 33-degree heat. I thought that he would break before the camera would break, and somehow they both survived. So that was kind of the other impressive thing about the measurements, is that all the devices still worked in some of those conditions, and then some other collaborators. So thank you.
Lots of fun of it. Have you looked at alternative ways to block out the sun, like a little robot with a ball on a stick around and gets the ball right where it needs to be?
I mean, that sounds awesome. Yeah.
I mean, it wouldn't work in all circumstances. It's just on the camera, so every camera can go with it. But it seems like
just because of the extra time and the
a lot of fisheye lenses, they aren't that good with their light absorption. Great light's a big problem.
Yeah, and I would say out of the 200 and I think it was 240 images that he captured, there were, so I guess maybe it was 130 or 140 images, and 100 of them were quite good. And plotted temporally, the ones he took the last week were 90% good. Yeah. And so it got better and better. And often it was because of things, like a lot of them were because like it was just too close to a building, or the clouds kind of moved in a weird way. But yeah. But yeah, because the farther away you have it, then the more shadow you have covering the whole lens. We definitely started that way with like a ball in the lab. And then we're like, oh, we can just bring it closer and closer and closer. Like, oh, that could be on the camera. But yeah. So I imagine you could just have a simple like minimization, right? Of like if you had a little sensor, like, or a readout basically from the camera. So if I could read out the EV hitting the camera, you would just go until it's the minimum. That would be my, like if you were thinking about putting it in like a remote application, automated application, I think that would be the way to do it, right? Is rather than trying to calculate. Yeah. So right now it has stops at 90, so it rotates 90 degrees and then stops. And so that's why we stuck with the 90, even though at the periphery it would be better to do it at kind of arbitrary angles. Because the mask is like this, it really doesn't need to be super precise, because you have a fair amount of buffer in this intersection, because right, the shadow band is right in the middle of this area. And especially if you went to like always orthogonal with one of them, like if you align one, I guess the phi angle, like if you always sort of like align the phi angle so it was straight and then did the other one perpendicular, there would be a lot of tolerance, I think. As the shadow band. Yeah. Well, yeah, so there's like I don't know, I'm not familiar with any that are that thin. Um, like the band is usually quite wide and so it eats up a fair amount. And or there's like that SP2 one that has the multi-sensor to like, but that actually has quite a big band and then it's using the difference. And so you can't actually recover all the imaging information, even if you can get the energy. Yeah, with the apparent side. Yeah, I mean, yeah. Yeah, I think like this, so the bespoke anodized aluminum thing is like definitely not so replicable, but I would imagine we could make a 3D printer template. Um, that would cost a couple $100 to print. Um, so I think making something particular to a camera would probably still win compared to off-the-shelf pyranometer band, but. Yeah, yeah. I mean, you get like this. You would end up with this kind of artifact unless you use uh, I mean, maybe like if you use like Adobe Smart Filling and something, you could do an even more kind of hybrid approach. Because for now, it's just really low tech interpolation. But yeah, I was thinking about that for the patterns. Like if you put I think the main thing is like adapting some sort of like AI filling thing to work in HDR. Because that also, there's the same thing with the lens flare removal, as all of those algorithms are not, like even the ones that are HDR aren't anywhere near solar luminance. And so they don't know what to do. It's kind of like, say as color models, they just break, they go the wrong way. Yeah. Well, so what I'm using it for is to make kind of high quality environment maps to do view study simulation. And so I wanted both accurate luminance values so I could use it as a light source, but I also don't want artifacts of what I'm seeing outside because I want to judge the quality of the scene and the artifacts that are introduced by shade cloth or Venetian blinds and not have to have those other things. Yeah, I think it has a pretty minor effect on energy, like having the lens flare, but it does have an effect on glare analysis. But with glare analysis, you can do basically the equivalent of like the peak extraction or something. Like there's simple kind of artifacts laden ways of doing that. Because like if you look at the like 300 candelas per meter squared, it's not gonna change your glare analysis. there, right? Like that's a really small error, but it's visible, especially if you run it through some, Pecan or some other human adapted tone mapping. Like it's going to become really present. No, I mean, I think the next step would be to make I think it would be as a 3D printed template, right? Because then you could easily adjust it to the lens diameter. And I guess you could even correct, like right now, the band isn't corrected to the equisolid because it's a signal lens, and so it has an equisolid projection, but it assumes an equiangular, right? Because it's not quite, it's also not quite right. But again, the tolerances are pretty high. So.